Hi everyone, today we are going to look at theories of Runge-Kutta method. Okay, so we'll start with rooted trees. So what is rooted tree? Okay, let T, this is a big T here, let T denote the set of rooted tree. A rooted tree is simply a connected graph where each vertex has a single parent. So this is the vertex, this is the vertex, this is the vertex, and so on. And each of these has a single parent. So this is a single parents. Okay. The order of the rooted tree is the number of vertices and is denoted by R tau. The trees up to 4 vertices are given by this. So this T here, the big T here, is a set of rooted tree. And we have all this T1, T2, 3, 3, okay, set of rooted tree, where these are all my trees, T1, T2, 3, 3, and so on. Okay, we will denote tau for the tree with only one vertex. Okay, so what is tau? Tau is a tree with one vertex. If Ti, where I from 1 to m are rooted tree, then we will have many trees. This thing is a tree formed by joining the roots of T1, T2, Tm to a new root. Okay, and then we'll learn also function on trees. So what is function on trees? In this section, some function of trees are defined. Okay, so the order of the tree R is given as, this is the order where R tau equals to 1. So the order function is given by 1 plus sum of all the order for all the trees from I equals to 1 to m. Okay, and then the symmetry of a tree. A symmetry of a tree, called as sigma, is given as sigma tau equals to 1. Then the symmetry is given by 1 plus product of sigma for the given trees. Okay, so to find the sigma of a tree, we must find the number of ways we can label the tree. And then we have the density tau. Okay, density of a tree is given by tau. This density of the trees are given by the order. This is the order of the tree multiplied by the density. Tree notation with the order of the tree RT, the symmetry sigma tau, and the density gamma t is given in table 1. Okay, let's look at example. Okay, so for this tree T11, the order is 1, the density is 1, and the symmetry is 1. Okay, there's nothing much we can say here. But for this tree here, we have 2 vertices. That means the order is 2. Density now will be 2 times 1, which is 2. And symmetry, number of ways you can label it, it's just 1. For this tree here, we have 3 vertices, that's the order. And then density, so 3 times 1 times 1. So we have 3. Now symmetry will be the number of ways you can label them is symmetry. Okay, I have 2 ways, so that's 2. Now for this case, this tree, order R is 3, density will be 3 times 2 times 1, which is 6. And the symmetry, there's only one way, okay, to label it. For this tree, this is an order 4 tree, 1, 2, 3, 4. Okay, the density will be 4 times 1 times 1 times 1, which is 4. Now the symmetry for this, we have 1, 2, and 3. Okay, there are 3 factorials way to label it. So 3 factorial will be 6. Okay, now for this tree we have 1, 2, 3, 4. Order is 4. The density will be 4 times 2 times 1 times 1, so which is 8. And that's only one. There's only one way to label it. Okay, in this case here, this is also order 4 for 4 vertices. The density will be, I have 1, 2, 1, 1, 2, 3, 4, 1, 2, 3, 1, 1, so 12. And I have 2 ways to label it, so it's 2. Now the last one, we have the order 4, 3. We have 4, 3, 2, 1. So we have 12. Density is 24. 12 times 2, 24. And that's only one way to label it. So this is how you find the symmetry, order, and density of a 3 up to order 4. Okay. Now we can also have some terms called elementary differential. Okay, elementary differential. The derivation of elementary differential up till 4th derivatives is given by this. So if y prime is equal to f, we can write this as a bold f. Y double prime is f prime y prime. Okay, so f prime y prime, f prime is f prime f, because this is f. Now y triple prime, okay, so we have, take the derivative of this one. Okay, this is like a product rule, so we want to have d over dy y double prime, okay, which is this one, f prime y f y, right? So taking the derivative will give you y triple prime. Now use the product rule. Okay, so what we have, taking the derivative will be f double prime y f prime. Okay, and then because this is implicit, differentiate inside will give you f y, and then plus, okay, this is now remain, taking this derivative will be f prime y, and the implicit will be f y. Okay, so how can I write this? I can write this as f double prime f comma f plus f prime f. That's how you get this term here. Now to take the 4th derivative, you have to take the 4th derivative for this one. Similarly to this, use the product rule. So what I use here is my product u v. Okay, so you can try that. Now how can I write down the elementary differential for this tree? Okay, this tree was 12 vertices. Now why is it 12 vertices? So you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices, right? So we start with, I have f triple prime for this one, 1, 2, 3, and then from here to here I have f prime, and then here I have 3, 1, 2, 3, so I have f triple prime. Here I have 2, f double prime, and f double prime for this one, and then I have f, 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 f. Okay, Okay, so how do you write it? So F T Y is yx, okay, function of t in x. Let's say we have this one equals to, so I will start with the root. For this term I have 1 2 3, okay, so I have f double prime ff, okay, and then comma f double prime ff, and then comma f prime, and then f triple prime, okay, f prime f triple prime bracket f f f, and then don't forget to close this bracket for this one and close this bracket for this term. So this is how you write elementary differential over 12 vertices. Okay, now we can also have elementary weights that are used to determine the order of the given Runge-Kutta method. The elementary weight of a tree is denoted by psi t. Okay, so let's look at the example for this tree with 12 vertices. Okay, we want to write down the elementary weight for this tree. Okay, so what we can do here, maybe I'll just write it here. So the elementary weight is given as, okay, the root will be B transpose, okay, and then here will be my A, this one will be my CC, this will be my A, this will be my C, C, A, C, C, C. Okay, so A will be the one that connecting from the root to whatever in between. Okay, so the elementary weights given by psi t equals to B transpose A C squared, okay, A C squared, and then A C squared, and then A squared C cube. Okay, this is your elementary weights. Okay, there's a reason why you are learning all these things. The theory of Runge-Kutta method, we'll look at it later. Okay, now from this from the elementary weight, the order condition for Runge-Kutta method can be derived by comparing Taylor series expansion of the approximated solution with the exact solution. Okay, so the order condition is given by psi t equals to 1 over gamma. What is my gamma? This is my density. The order condition is important to determine the order of any constructed method. Okay, so let's look at how we can derive the order condition. For order 1, for 1 vertices, so we write it B transpose, so which is B1 equals to 1. This is the order condition for order 1 method. Now for order 2 method, okay, so before we do order 2 method, look at this example. Show that the Euler method defined by Boucher tabular below is of order 1. How can I show Euler method is order 1? So what you do here, B transpose E equals to 1. So E is the elements of 1. Okay, B transpose here is 1. So we have 1 equals to 1. So we can say that the method is order 1. Now the order condition for order 2 method. So order 2, we have 2 trees. Okay, we have 2 trees. Okay, that satisfy order 2 condition. So one is this one, and then we have the tall tree, this one. So this is just B1. Okay, just B, this is B transpose C. Okay, there's no A, B transpose C. Okay, so what we have to satisfy b1 here, okay, we have to satisfy b1 plus b2 equals to 1, and then b2 c2 equals to half. Okay, this is the order 2 condition. For example, show that the explicit midpoint rule is of order 1. I'm sorry, order 2. Not order 1, order 2. So we have two conditions. What are the conditions? So we have b1 plus b2 equals to 1, b2c2 equals to half, right? Okay, we can show that this is b1, this is b2. So 0 plus 1 is 1, and then b2 times c2. This is the c1, this is c2. So b2 times c2 is half. So satisfy two conditions, so we can say the method is order 2. Now show that the explicit trapezoidal rule is of order 2. So similarly, to satisfy order 2, we have two conditions. Okay, two conditions, and they are, what are the conditions? b1 plus b2 equals to 1, b2 c2 equals to half. Okay, this is my b1, b2, c1, c2. Now I can see that b1 plus b2, half plus half is 1. Satisfied. b2 times c2, half times 1 is half. So the method is order 2. Okay, look at this one. To satisfy order 3 method, you have to satisfy 4 conditions. Okay, to show the method is of order 3, you need to satisfy 4 conditions, and these are the conditions. b1, b2, b3 is 1, b2, c2 plus b3, c3 equals to half, b2, c2 squared plus b3, c3 squared equals to 1/3, b3, a32, c2 equals to 1/6. Okay, so these are the conditions to satisfy order 3. So for example, show that the method is of order 3. Okay, how many conditions we need to satisfy? Satisfy 4 conditions. And what are the conditions? Number 1 is for this b1 plus b2 plus b3 equals to 1. And then we have to satisfy this tall tree, which is b2 c2 plus b3 c3 equals to half. And then we have to satisfy this bushy tree, okay, such as b2 c2 squared plus b3 c3 squared equals to 1/3. And then we have to satisfy this tall tree, okay, which is b3 a32 c2 equals to 1/6. If you can show that all these satisfy, then you can tell the method's order 3. For instance, we know that this one is b1, b2, b3. This is c1, c2, c3. And this is my a32. This is my a21, a31. Okay, so let's see that. b1 plus b2 plus b3 equals to 1. 1/4 plus 0 plus 3/4 is 1. Okay, that's good. b2 c2, 0 plus b3 c3. So what is b3 c3? We have 3/4 plus multiply 2/3. So we have half. So satisfy. And then b2 c2 squared. Okay, this is 0, this is 0, this is 0. Now what we have here? b3 c3 squared. So we have 3/4 plus 2/3 squared. 3/4, 4/9. So what do we have? 9 divided by 3 is 3, so 1/3. Satisfied. Now to find B3A32C2, we have B3 is 3 over 4, A32 is 1/3, and C2 is 2/3. Okay, cancels out, 2 and 2 give you half, and then 1 over 2 times 1 over 3, 1 over 6 satisfy. So since it satisfies all the 4 conditions, the method is therefore order 3. Okay, I hope you're getting there. Now similarly, we want to say that write down the order condition for 4-stage explicit Runge-Kutta method of order 4. Okay, write down the order condition. Okay, so we know that for order 4, we have 8 threes. How many threes? 8 threes. Okay, how do I know that? Let's sketch. Let's sketch. We have 3 this one. 1, 2, 3, 4, 5, and then we can have this one, 6, and then we can have like this, 7, and last one is my tall 3. There are 8 ways, so there's no other way to determine the trees for order 4. Okay, there's four ways to get it. So for this one, the order condition will be B1 plus B2 plus B3 plus B4 equals to 1. Okay, this one always, the rule will always be B transpose. Okay, this one I can write as the elementary weight B transpose C. Okay, so it will be B2C2 plus B3C3 plus B4C4 equals to half. Okay, remember, why is it half? Because we know that the order condition is given by 1 over density. Density is how you find density. So this is 1, this is 2, 1, 2 times 1, 2. 2 times 1 is 2, so 1 over 2. For this one, let's label it B transpose CC. Now the density is given by 3, 1, 1. So we have 1 over 3. Okay, but how do you write it? So it will be B2 C2 squared plus B3 C3 squared plus B4 C4 squared equals to 1/3. Now the elementary weights I can write as B transpose AC. Okay, and then the density will be 3 times 2 times 1, 6. So we have 1 over 6. But how can I write the condition? Okay, the condition will be B3A32C2 plus B4A42C2 plus, erase this, plus B4A43C3 equals to 16. Okay, so we have B transpose AC. So it's okay to have BAC, BAC, BAC. Okay, now this one, it must have B transpose C cube, and the densities are 4 times 1 times 1 times 1, so it will be 1 over 4. Okay, so I can have B2C2 cube plus B3C3 cube plus B4C4 cube. Okay, now for this tree here, what's the density? 1, 2, 3, 4, 1, 2, 1, 1. The density is 8. Okay, 1 over 8. Then how do you write it? We have B transpose C A C. So I just look at this equation here, and then don't forget to add A in between. So I have B3 C3 A3 2 C2 plus B4 C4 B4 C4 A4 2 C2 plus, it's getting longer so I better erase this, plus B4 again, plus B4 C4 A4 3 C3 equals to 1 over A. Okay, now for this 3 here, we have B transpose AC squared. Okay, what's the density? 4 times 1, 2, 3, 4. 4 times 3, 1, 2, 3 times 1, 1. So it's 12, 1 over 12. So what we do here, okay, we look at this term, this 3, and then we have C squared. So we have B3A3 2C2 squared plus B4A4 2C2 squared plus B4A4 3C3 squared equals to 112. And then our tall 3, so we have B transpose A C. So we will have B4 A4 3 A3 2 C2 equals to 1 over 24. So this is the order condition for order 4 method. Order 4 methods. Okay, so you have to satisfy 8 conditions. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can check by doing that. Okay, check for this method whether the 4 conditions satisfied or not. Okay, let's move on now. This is the order condition for up to 4 trees. I've shown you until here. Okay, I've shown you until here. So this is how you write the order condition for 4. A tree with 4 vertices. Okay, remember this big A here, because you will have a summation. So all this have a summation. Okay, all this term, there is a summation here. Okay, but usually we don't write the summation because we know it's a matrix. So you gotta be careful when you're doing multiplication for the tree. Okay, so these are the theory of Runge-Kutta method. So I hope you will study them again and feel free to leave a comment. That's all for today. Thank you. Bye. If you recall, the row sum condition, what's the row sum condition say? The row of C, okay, the Ci is equal to the summation of Aij for j equals to 1 to s. Okay, where I start from 1 to up to s. So meaning that to get A, the sum of A is equal to C. Okay, but we can write it in this because we know this is just one stage, so this C is equal to C. Okay, that's the easy way to find it. Okay, so what is the condition to satisfy order 1? There's only one condition to satisfy order 1. You look at it in the last week video, which is this tree. This is the only tree for order 1. Okay, which is B equals to 1. Okay, so what we have here, so if B equals to 1 and C equals to 0, what we have? We have the explicit Euler method. Okay, but we can also have B is 1, A and C is 1. So this is what we have, implicit Euler or backward Euler. Okay, now to satisfy order 2, now so we have this. So order 1, there's two methods, which is explicit Euler and implicit Euler. Okay, now to construct an order 2 method, okay, now look at this order 2. So we have, by right, we have C1 and C2. Okay, this is C1. Okay, but in this case the row sum condition holds, so this is C2. Okay, so what we have here, by referring to the, so we look at the order condition for order 2. What are the order condition? So for order 2 method, we have this, we have to satisfy order 1 condition, and these are the trees involving order 2 method. Okay, so what is this? This is B1 plus B2 equals to 1. Okay, and then this one will be B2 C2 equals to half. Okay, let's see if you want to construct this method. Okay, what we do here, let's check. So what can we do? What can we find out from here? Okay, so we can look at another condition. Okay, let's refer to another tree. Okay, we know that this tree will not be satisfied. Okay, and then we can have another condition. Let's add another condition. Okay, so the other condition is this one, where this is the order 3 condition actually, so which is B2 C2 squared equals to 1/3. Okay, first let's say the choice of C equals to 1. Let's say my C2 equals to 1. So what do I have? I have a method like this. Okay, so this C1 here will be 0. And why is that? Because of the row sum condition. If my C2 is 1, it will be like this. So what happened here? I have B2 C2 equals to half. Okay, so B2, if C2 is 1, we have B2 equals to half. B2 is half. Now with this condition, if B2 is half, B1 is also half. So we can have a method called the trapezoidal rule. Okay, the trapezoidal rule. Now we can also have another method. Okay, another method. So let's look at the table again. So which is 0 0 0 C2 C2 0 B1 B2. Now if we choose C2 equals to half, what do we have? We have a table like this: 0 0 0 half half 0. Now we know that B2 C2 equals to half. If B2 C2 is half, what is B2? 1 over 2 times with 2, half. Bring it to your right hand side. Okay, where B2 equals to 1. If B2 is 1, okay, now remember we have the condition for this one, which is B1 plus B2 equals to 1. If B2 is 1, now B1 is 0. So I have 0 1. Now what method is this? This is my explicit midpoint rule. Okay, so the two methods that we can construct by looking at the order condition. Can we have any other method? Okay, can we have any other method? Okay, so to check any other method, you just have to satisfy the condition. Sometimes you can use like the order 3 condition, this one, because we know that this method will fail for order 2. For instance, if you check b2 is half, right? So we have half, so we have 1 over 2, that b c2 squared, c2 is 1 squared, which is not equals to 1 over 3. So we know that the method only satisfy order 2 condition, so the method is order 2. Okay, now you can ask me, why can't okay, why can't c2 equals to a quarter? Okay, why can't c2 equals to a quarter? Okay, let me show you why can't c2 is quarter. So if c2 is 1 over 4, we have b2 c2 equals to half. b2 will be half times by 4, where b2 is 2, right? And then to find b1, we have b1 plus b2, 2 equals to 1. So b1 equals to 1 minus 2, which is negative 1. So you will have a method like this: 0, 0, 0, a quarter, 0. Okay, b1, negative 1, 2. Now this method, okay, it does satisfy order 1. It can satisfy order 2 because b2 c2. Okay, b2 c2. But the quadrature weights that have negative here is not good. Okay, it's not good. So we want to have a positive number for your b. So this is not a suitable method. If you get a negative 1 here on the b's, so they are not good. Okay, is there any method that have something like this? I never came across a method that can have negative 1 here. Okay, now let's move on to order 3 method. Okay, construct a 3-stage explicit Runge-Kutta method given by this. Okay, this can be very tricky. This can be very tricky. So what we can do here, we know that we can, for 3-stage method, how many order condition does it satisfy? Okay, let's see. We have this 3, and we have the tall 3, and then we have the bushy 3 for order 3, and then we have the tall 3 for order 3. Is there any other ways? No. So there are 4 conditions to satisfy order 3. 3-stage method. Okay, we have 4 conditions. Okay, so we know these are the same. And C3 will be C3 minus A. And then if this is my B1, B2, B3, so we know that for this condition, B1 plus B2 plus B3 equals to 1. Okay, now for this condition, okay, is B2 C2 plus B3 C3 equals to half. Okay, and then for this condition we have B2 C2 squared plus B3 C3 squared equals to third. And then lastly we have B3 A3 2 C2 equals to 1/6. Okay, so what we can start by we can start by putting some values to find out what is B1, B2, B3. So I can start by finding my C. Okay, so let's say I have C. Let's say my C1, which is 0. Let's say my C2 equals to half. C3 equals to 1. Okay, so what can we get from here? Let's look at this condition and this condition. Okay, I'm writing it here. So we have C2 equals to half, C3 equals to 1. So B2 C2 plus B3 C3 equals to half. So we have C2 is half, so we have B2 half plus B3 equals to half. So multiply everything by 2, I have B2 plus 2B3 equals to 1. This is the first condition. Now we have the other condition for the bushy tree. B2 C2 squared plus B3 C3 squared equals to 1/3. So we have B2 C2 squared plus B3 C3 squared equals to 1/3. So B2 C2 is half, so we have half squared plus B3 C3 is 1 squared equals to 1/3. Now what we have here, B2 1/4 plus B3 equals to 1/3. Multiply everything with 4. B2 plus 4B3 equals to 4/3. This is equation number 2. Now equation 1 minus equation 2. What do we have? This and this cancels out. 2B3 minus 4B3 equals to 1 minus 4/3. Okay, I'm just going to continue here. So we have here, this is negative 2B3 equals to negative 1/3. Okay, so we can find B3. B3 is 1/6. Okay, that's a good sign, right? We have obtained B3, which is 1/6. So B3, I'm just going to write it here. We have B3 equals to 1/6. Can I find, look at this condition here. Okay, maybe this one. Equation 1 becomes, if B3 is 1/6, so I have B2 plus 2, B3 1/6 equals to 1. So B2 equals to, what is this, 1/3? Okay, so 1 minus 1/3, so we have 2/3. Can I find B1? We know B1 is, for this tree, we have B1 plus B2 plus B3 equals to 1. So B1 will be 1 minus B2, 2/3, minus B3, 1/6. Okay, there's a mathematical here, calculation that you need to find. So times by 2 times by 2. So I have 6 minus 4. Okay, 6 minus 4, which is 2/6 minus 1/6. So B1 is 1/6. Okay, so we have obtained B1, B2, B3. So I can summarize this this table here with the condition that I have obtained by using, okay, let me just write the proper table now. So what I have, if I choose my C2 is half, C3 is 1, this is 0, this is half, 1 minus A. What is A? We don't know. Okay, we don't know A, but I know this is my B1, B2, B3, which is, I've already obtained here. B1 is 1/6, B2 is 2/3, B3 is 1/6. So I have 1/6, 2/3, and 1/6. Okay, now this is 1 minus a, and 0. This is 0. Okay, so how to find a? We know the last tall tree here is given by B3, A32, C2. B3, A32, C2 equals to 1/6. Now this is my A32, right? Okay, so I know what is B3, so I have 1/6, A32. Now C2 is half, equal to 1/6. So what do I have here? 1/12. So A32 equals to 1/12. So bring it here will be 12/6. So A32 equals to 2. So I have 2 here. Now what is C3 minus A? 1 minus 2, which is -1. So this is my RK3 method. Okay, RK3 method consists of this element. Okay, 0, half, 1, and I'm sure we have checked this method earlier on. Okay, it's in the beginning of, I think it's on slide 20. Let's check. Okay. Okay, so maybe it's here. Somewhere here. Maybe further up. Slide 20, 17. Yeah, slide 20. Okay. For this method. Okay, for this method, what is the butcher tabular for this? So this is 1/6, 2/3, 1/6, and my C, this is 1 here, this is half here. Okay, there's a half here, and then 0 here. Continue to find the A. So to find the A, you look at the big Y. So we have 0 here. For Y2, I have half. For Y3, I have -1, 2, which is exactly what we get. Okay, exactly what we got earlier on. Okay, now you can also find another method for order 3. Okay, but I'm not going to show you, but you can try to find another method for order 3.